Alright, so in this video, I'm gonna be explaining another important article on domain adaptation with the title T-SVDNet, Exploring High-Order Prototypical Correlations for Multi-Source Domain Adaptation. So this paper in 2021 from this laboratory. Most existing domain adaptation methods focus on adaptation from only one source domain. However, in practice, there are a number of relevant sources that could be leveraged to help improve performance of the target domain. We propose a novel approach named T-SVDNet to address the task of multi-source domain adaptation, which is featured by incorporating tensor singular value decomposition into a neural network's training pipeline. Overall, high-order correlations among multiple domains and categories are fully explored so as to better bridge the domain gap. Specifically, we impose tensor low-rank constraint on a tensor obtained by stacking up a group of prototypical similarity matrices, aiming at capturing consistent data structure across different domains. Furthermore, to avoid negative transfer brought by noisy source data, we propose a novel uncertainty-aware weighting strategy to adaptively assign weights to different source domains, and sample based on the result of this uncertainty estimation. You see the framework of T-SVDNet that we have given M label source domains S1, S2, S3, S4, Sm, and unlabeled target domain T, which is our target domain here. We first extract features for input images and compute prototype. So once we get these prototypes for both source and the target, these are our prototypes that we need them. And the relations between pairwise prototypes are modeled by a group of similarity matrices. Then we stack these prototypical similarity matrices into a three-order tensor G, on which tensor low-rank constraint is imposed in order to explore high-order relationships among different domains. And finally, together with the low-rank regularizer, the model is effectively trained in an alternative optimization strategy. So in the MDA setting, there are M-labeled source domains and an unlabeled target domain. Each source domain contains N sub M observations, where Y sub I is the desired label, while in the target domain, the label is not available. Most existing MDA approaches can be formulated as the following mapping, where M is trained on both labeled samples in the source domain and on labeled samples in the target domain. In the proposed T-SVDNet, we first map input image into latent space through a feature extractor. So then we get the prototype, we can compute the prototype for each domain. And this one is the set of training samples, because we are drawing from these samples. So it is noteworthy that for unlabeled target domain, we first assign pseudo labels Y sub I hat to samples with high classification confidence. Specifically, we map each image into target domain into a classification probability vector P sub I. Then we set this threshold tau, selecting the confident predictions as pseudo labels. In order to reduce the randomness in sampling of each mini batch and stabilize the training process, the category prototypes are updated according to exponential moving average method. Then we employ the Gaussian kernel, this Gaussian kernel here, to model interclass relationship. We construct a series of prototypical similarity matrices. And these are category centroid. For example, for a particular class C sub I or C sub j, we can see the Gaussian kernel. And then, unlike conventional methods only considering pairwise matching, we achieve high-order alignment of all domains at the prototypical correlation level. Specifically, we stack prototypical similarity matrices into a 3-order tensor, along with the third dimension, where C and M denote the number of classes and domains. Then we impose the tensor low-rank constraint on the assembly tensor in order to explore high-order correlations among domains and enforce the relationship between categories to be consistent across domains. So what is this TVST? Given a tensor, the tensor singular value decomposition of that is defined as just a finite sum of outer product of matrices. You know that U and V are orthogonal tensors, and S is a tensor with size n1 times n2 times n3, each frontal slice of which is a diagonal matrix. So this T-SVD also can be computed more efficiently in the Fourier domain, of course. And then we have tensor rank. The rank of a tensor is a vector with the case element equal to the rank of case frontal slice. In the view of each frontal slice of tensor G only contains information from single domain. We rotate it horizontally or vertically to obtain tensor of rotation. In this way, each frontal slice will involve information from different domains. At the end, imposing tensor low-rank constraint on the rotated tensor benefits the exploration of high-order relationship among different domains. Now we are dealing with this uncertainty. Instead of equally treating each source domain and sample, we propose a novel uncertainty-aware weighting strategy to adaptively balance different sources and alleviate negative transfer led by noisy data. Considering that data uncertainty could capture the noise inherent in the data, for example, it reflects the reliability of output, we could weigh different sources and samples based on the result of uncertainty estimation. The output of the network is modeled as a Gaussian distribution parameterized by this this is mean and variance of this normal distribution, Gaussian distribution. So the mean is acted by original feature vector, while the variance quantifies this uncertainty of training samples. So this can be interpreted as a Boltzmann distribution or Gibbs distribution. And sigma squared, this variance works as temperature for rescaling input. So we can have this log likelihood of the output. H sub c is just the cis element of the vector H. Now we have this total classification loss, where LC here is just the classification cross entropy loss with HXI not scale. And noisy data with large uncertainty would be assigned less weight. For example, 1 over sigma I2. And the derivation process is in the appendix of this paper. So this is just cross entropy. And we introduce a simplifying assumption in the last transition. The overall objective function of the proposed model is like this. And this one, this symbol here, denotes two operations, tensor rotation and tensor nuclear norm. And psi represents the operation of stacking up all domain-specific prototypical similarity matrices into a tensor. To optimize the objective function, objective function, we first introduce an auxiliary tensor A, this auxiliary tensor, to replace G. So we just minimize the difference between them. So instead of G, we are working on A now. And eta is just a penalty parameter. It starts with a small initial positive scalar, gradually increasing to maximize truncated value. The parameters of feature extractor, classifier, and uncertainty predictor are updated through gradient descent with auxiliary tensor fixed. When network parameters are fixed, we optimize the subproblem, and we solve the problem in Fourier domain with basic procedure, similar to algorithm 1. We first transform tensor to Fourier domain, perform SVD on the case frontal slice. Then each frontal slice of auxiliary variable can be updated by shrinkage operator in the Fourier domain. So this shrinkage operation on G in the Fourier domain is this. D is just singular value shrinkage operator. And finally, updated A is obtained by inverse fast Fourier transform from A. So this is how we are getting this A. After getting A, then we do this. So we do SVD, we obtain A, we do rotation, and finally we get the eta. And you see the uncertain distribution of different domains and digits 5. Also, uncertain distribution of single domain varies with increasing noise intensity on MNIST.